Welcome to our exploration of one of the most fundamental laws in physics, Newton's law of universal gravitation. Every object in the universe attracts every other object with a force that depends on their masses and the distance between them. Let's start by understanding what makes this law truly universal. The most remarkable thing about gravity is that every single mass in the universe attracts every other mass, no matter how large or small. This gravitational force always acts along an imaginary line, connecting the centers of the two objects. Here we see two masses attracting each other with equal and opposite forces, along the line connecting their centers. Now let's look at the precise mathematical form of this law. The gravitational force equals g times the product of the two masses, divided by the square of the distance between them. F represents the magnitude of the gravitational force acting between the two objects. G is the universal gravitational constant, which has the same value everywhere in the universe. The value of G is approximately 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared. M1 and M2 represent the masses of the two objects, measured in kilograms. R is the distance between the centers of the two masses, measured in meters. One of the most important features of gravity is how it changes with distance. If you double the distance between two objects, the gravitational force becomes only 1/4 as strong. If you triple the distance, the force drops to 1/9 of its original value. This graph shows how gravitational force decreases rapidly as distance increases, following the inverse square law. Mathematically, we say that force is inversely proportional to the square of the distance. Let's explore how mass affects gravitational attraction. The gravitational force is directly proportional to each of the two masses involved. This means F is proportional to M1 and F is also proportional to M2. When we increase the mass of one object, the gravitational force increases proportionally, as shown in this comparison. Let's apply this law to calculate the gravitational force between Earth and a person. Suppose we want to find the gravitational force between Earth and a person with a mass of 70 kilograms. Earth has a mass of approximately 5.97 times 10 to the 24th kilograms. The person has a mass of 70 kilograms. The distance is Earth's radius, which is 6.37 times 10 to the 6th meters. Substituting these values into our formula, we get the gravitational constant times the product of the masses, divided by the radius squared. This gives us approximately 686 newtons, which is the person's weight on Earth's surface. This diagram shows how Earth pulls on the person with a force of 686 newtons, which we commonly call weight. Let's summarize the important properties that make gravity unique. Unlike electric forces, which can attract or repel, gravity always attracts objects toward each other. Gravitational force extends infinitely through space, but it gets weaker as objects move farther apart. Every object with mass experiences and creates gravitational force, regardless of its composition. This illustration shows how a central mass attracts all surrounding masses, demonstrating gravity's universal attractive nature. Let's review the key points about Newton's law of universal gravitation. The law is expressed by this elegant equation relating force to mass and distance. Remember that every single mass in the universe attracts every other mass with gravitational force. The force gets stronger with more mass and weaker rapidly as objects move apart. This simple law explains countless phenomena, from planetary motion to ocean tides to why objects fall. Ultimately, gravity is the force that shapes galaxies, solar systems, and the large-scale structure of our universe.